Auziți?
Așa aveam trecut aici.
Doamnelor și domnilor, numele meu este Marius Pană, reprezint compania Spearhead Systems în calitate de partener unic și distribuitor în România, atât cât și Republica Moldova și sperăm în curând câteva alte țări în apropiere. Am să fac o introducere foarte scurtă înainte să vi-l prezint pe invitatul nostru. V-aș spune o foarte scurtă poveste de ce am realizat noi lucrând cu SGI în ultimul an și jumătate. Și aș sumariza experiența noastră în două cuvinte: experiență și consistență. Experiență deoarece când vorbim despre HPC, SGI-ul este renumit, este cunoscut, este în evidență prin ceea ce face acum, ceea ce face încă de la început. Consistență deoarece am avut plăcerea să lucrez cu arhitecți, ingineri, oameni care lucrează cu SGI de peste 20 de ani. Experiența pe care o aduc și o au și o împing în soluțiile lor este de neprețuit. Nu merge, când vorbim despre HPC, să adunăm componente de calcul generale și să zicem că am făcut un cluster HPC. Problemele de care ne lovim sunt foarte tehnice și atunci experiența celor de la SGI este de neprețuit. Fără a mai intra în alte detalii, îmi face o deosebită plăcere să vi-l prezint pe partenerul nostru Michal Klimes, care are o experiență de peste 18 ani la SGI. Mulțumesc frumos!
So good morning. I will disappoint you. I will not speak Romanian. So I hope everyone understands sufficiently English. And so I'm with company 18 years. So from the all graphic history, as you know, we have been mainly graphic company at the beginning. And why we started with the big servers? Because our graphic was much faster than the data we can get, right? So we start to build up the 18. And as you know, today practically everything in the development and in the science is, interest to develop in the virtual stage, right? Not really doing the prototype, not doing the product and understand the word. And if, let's say, many years ago, people understand the things in millimeters, and today we are going to the femtometers, right? And if many years ago we tried to understand our planet, we currently try to understand all the universe. So things are going everything opposite and everything getting big. So HPC is big data. I use a lot of pictures because sometimes, HPC is kind of a, let's say, term. Making big systems is not today difficult, honestly, because you can take a lot of components, a lot of nodes and put it in one room, but making it the infrastructure that, for example, you can all keep with the power, you can all cool it, and then you can use it efficiently, that's really the challenge. Some trends, right? Why we do what we do. So if you look this, and there is no secret data, you can find that there is a top500.org website where the, let's say, largest machines every time the top 500 are consolidated. So you can search the website, you can look who is having what, you can look the efficiency, everything. What is interesting here, that's the two graphs. One is the system, number of the system per country and installed performance. And if you see, you would not be surprised seeing US. But you can see, for example, how China did in recent years. And I'm showing this very often, it's very important. If you see what are the countries, right, that's one of the best developing countries, the economy. So generally, you can today measure the competitiveness of the country and nation by the install HPC, let's say, performance. Not necessary, right? So you cannot compete with US, we cannot compete with US. But if you probably would normalize the installed performance per inhabitant, you would get pretty, clear indication how the country is doing. And you can take two approaches, right? One approach is, so all scientists and universities, they have to present the project, and then they will get money. Or some governments do it opposite. They say, here's the money, we made the center, do it, right? Germany is this way. Germany is having several national-wide centers without permanently, giving them money. So this is, very important. There are not small things on this planet, so I agreed with the lady will be here, so if we can click on it. So this is the global warming. And that's a picture from NASA. You know, we don't compute global warming. NASA is very close to us. And as you see, it started in 1870. So from the time when NASA collect the data, right? So they occupy the North America people and they start to collect the data. And the difference is, right, as you see, so no change mean between this 0, this is the number of the change degrees, right? So if you see around Florida, you know, that's where all the hurricanes, right? Now, if the sea is 1.5 degrees warmer, you know, they get maybe twice hurricanes. If you want to look at, and why they go all the history to the future? Because they want to verify the model makes sense, right? So if you see how we end up, in Canada, they will have nice weather, right? They will have about 8 degrees more than today, right? So that will be close, like Mediterranean. It will be a little hotter in Florida. It will be cooler here. And that's honestly, that's significant things because the climate on the planet is not involved by this temperature, but by the flows in the sea. And this change in the sea will make significant things. So as you see, this is the model calculated for approximately last 200 years, right? With all simulation, with all the planet. So you can imagine it's a pretty sizable model. What makes the big machine big, right? So if you go 64 cores, that's easy. Anyone can do. There is no really special knowledge needed because here you see we have some technology involved from us, right? If you get to 256 cores, you suddenly see the things are quite different, right? And you continue. You know, NASA is having currently, our latest machine is 1.7 petaflops, which probably would be, I don't know, few 100,000 cores, right? So today, to build a big machine, the HPC is really how to make the cores working together. We have Intel here, they make cores. They are adding the cores all the time, more to the CPU. Honestly, the HPC today is the science how to make these all cores working together. This is tested, by the way, on the OpenFOAM, which is the open source fluid dynamics package. Then a lot of discussion about the consumption, right? So here you see example. So if the machine is not doing anything, it consumes, it's about 1 rack. So it's consumed about 15 kilowatt. If the machine is fully utilized, and LINPACK is one of the theoretical benchmark very you often used in the industry, it tells you very well about the peak performance. It doesn't tell you very much about the real-time performance because this is not testing very well I/O. This is stressing the CPU. Why the LINPACK is so popular? Because that's the parameter why the top 500 is measured. You know, so everyone will run the LINPACK because they want to be somewhere in the top 500. It's very prestigious. Then you have some other more realistic up to Fluent, you know, which is a typical fluid dynamics. So this, you see, you know, this machine are stressing also much more I/O. So the CPUs are not so much stressed or utilized. So the overall performance is much lower. Again, this is important because, as I said, it's a 1 rack today is 30 kilowatt, right? So if you take 10 racks, it's 300 kilowatt, right? If you take 100 racks in the NASA size, right, you are about 3 megawatt. And don't expect this is very surprising. So, say we are supplier to Škoda. You know, I'm from Czech Republic. They just opened the tender, the center 2 times 4 megawatt, you know, for the power. So this is, you know, all these numbers together, right? And we speak currently only about the, let's say, usage of the power by machines. Another interesting picture, you know, so where's the performance? So you take the Fluent, you know, you take the fluid dynamics over the track body, not very complicated, right? And you see, you can do, you know, you calculate this model on 128 cores with some speed. You go 256, you get better. But you see things are getting much worse in 512, and in 1024, you get, you slow down the machine, right? And there's 3 important categories. So this is, you know, what is the MPI or reduce. So this is the communication. This is, you know, the different things in the communication. And this is really where the CPU is computing. So you see, and that's what is the problem, right? Because with the number, of course, you can imagine it's like an army of the slaves, right? Or maybe workers, let's be correct. So you shout on them, right? And if you shout on, let's say, 200 people, do something, right? Take the brick, and they will tell you, I have the brick, right? You collect the data easier. If you shout on 1,000 people, take the brick, and you have to wait up till the last one, take the brick, and tell you, I have the brick, right? So you get much more problem. And you see that, you know, if we normalize it to the 100, so at that time, you see, with every number of cores, you know, the effective performance used for the computation is lower and lower, and the things, you know, the communication around is growing up. So this is again, you know, one of the critical things in the computation. And as you see today, we are this, you know, at the 1,000 cores. That's practically nothing, right? If you consider it's just about 10 cores per CPU, right? So we are about 100 CPU. No, it's not HPC system yet. Another interesting picture from the trends. So that was measured. It's not on the latest machine, but we work, as you have recognized, you know, we work very close with all these big companies, you know, NASA, developers, because we want to understand where is the bottleneck. You know, it's not like we want to make the system which will perform and you can connect. We want to understand. So this is like for 1 month they measured in LRZ where the application missed the level 3 cache. So that means at that time they have to go out to the memory, right? And you see very, you know, interesting behavior. So there are a group of applications here, you know, not missing often here and here. Right, there's nothing between. So it tells you it's not really HPC load, it's not something general, right? It's really quite specific. And here you would do much better with shared memory because you miss the cache load many times. Here you might be pretty well with the cluster type of the machine, right? So again, people say, you know, and the Chinese made, I don't know if you look top 500 again, the China is having, I think, in the top 5, I think they have 2 or 3 computers. They are very big, you know, but there was recently, there is a magazine, you know, Electronic HPC Wire, and recently they said it's, you know, now they have like 10 lines highway and they use tractors to go on over it, right? So it's really important. So how we turn all this observation to some technology, and I'm not going really, so we do a lot of computers, you know, as you can imagine. We will today speak about 2 of them. So SGI UV2 is ultraviolet, most flexible system as we call it. So as I mentioned, you know, we have a commodity clusters. If it's commodity, non-commodity, it doesn't matter, commodity. And we have a shared memory platform. Clear to you, in cluster, every node, it's separate computer. But that means you are limited everything to that node. Right? If you want to go to the other node, you have to use all the knowledge and the application to synchronize these things, how to get them efficient and together. We believe it's better, right? So everyone knows how to use the normal PC, everyone notebook. You know, what about if notebook can have 2,000 cores and 16 tera memory, right? Big notebook can be pretty fast, and that's generally what we are investing for it. Here, these systems are very, very good. And we make them, you know, it's not any conflict in it, especially where the vendors are, let's say, programming the system directly to optimize it. So if you look, ANSYS, Fluent, a lot of the application. These systems are very often used by people who has a big data and they like them to have in memory. So currently all the genomic research is very, very valuable for it. All the, let's say you can call it special HPC, all the CIA, KGB, you know, spying stuff, you know, there's a lot of this because you can imagine that people, they load all the internet traffic, you know, if you write how to build a bomb, you can be sure there is already some red screen somewhere. And so this is, you know, extremely good for spying. I don't know how often you spy. It's pretty good for it. And so we do that system already for some time. It's important to say that the NUMA, the non-uniform memory architecture, it's a research from the Stanford University. And it's available for other people. You know, it's nothing proprietary. What is our development is how to take this NUMA implementation to the actual system, right? So the things which you will see, and here's, let's say, what we do, where we are today, you know, a lot of memory. It's a lot of memory. You know, when you have so much memory, it's complicated because you can have a big model, but what if the one DIMM of memory fail, right? All the machine go down, or not the machine, but the application. And normally the people, you know, from the environment like telecom complain, our machine cannot go down. You know, the HPC people complain a lot as well, because if they compute something for 1 week or for 2 weeks, right, and the system is going down after 10 days, they are pretty upset because of one DIMM. So we have a special built-in algorithm. We check the health of the memory. So this machine will never fall on the memory, for example. You know, we just eliminate the memory, so you can maybe run it for a year. You will have then 64 terabyte minus some gigabytes. And that's generally what we do. So we take the CPU, standard component, standard CPU. We take it from Intel or from AMD, but you know, but we develop our hub, right? So we don't think the Intel chipset is so good. So we develop for the big thing our own chipset, right? That's really what we do. So we develop special chips, and then we connect this like the, let's say, switches, crossbar switches. Because once you go to the big configuration, if you would go ring, right, there was some ring NUMA implementation, then there's a lot of traffic. You know, you can imagine. We go crossbars because then we somehow guarantee, even for the big configuration, that, for example, the latency to the further distant memory is still acceptable. And that's, you know, what we do. You know, it doesn't sound so exciting. It is pretty exciting because the chip is very big, right? And we have in this, what I mentioned, this, or about this memory. So if we have such a big memory, you need to understand, it is important to know what you have where in the memory. And that's, we have a special memory management. So it's, if you would make a normal machine again, you know, like a smaller SMP, and you would not use our chipset, then the CPU is taking the information and management of the memory. So they move the memory. He shout, if he needs a memory which is not close to him, he shout and someone say, oh, I have this data, what you want? We here, we know all the time where is what we want, right? And because also all these memory transfers, because as the machine run, and as we understand what the application is doing, we try to move data from the, for example, remote memory to the chip which is supposed to compute that. So again, another optimization of this. Called that memory offload engine, MOA. You know, it's a small characters, very important thing. Very important thing. We'll show you here, right? So if you use the memory offload engine, we get things 3 times faster in the latency. And here you see the result. You know, if you use some benchmark, how much number you get with the memory offload engine disabled and enabled. So that's again another thing, and another graphic form, right? That's with the standard, with the memory offload engine. So you see the MPI barrier. And that's only just, you know, technology. So it's a current implementation of chipset. So you can imagine this, as we are developing it, it costs some money, right? So everyone say, you know, it's a great technology, you are more expensive. Yes, we are more expensive. So by this step, you know, from here to here, we try to get it cheaper. Why then it makes sense to you, you know, to consider machine? Because sometimes people say, if I get the cheapest machine, it's excellent. But then you don't include every time in this computation how much time then you spend, for example, to optimize the code for the cluster. Because, as I said, in this memory, in this machine, you really don't need to optimize. It's still, you know, you have to write it intelligent, but it's much more easier. As you can imagine, the machine is having some box, right? So that's the implementation. You see we have a lot of throughput, you know. The aggregate, you know, bandwidth, for example, 100 to 7 gigabytes per second. It is important, you know. The big machine is all about all the interconnect infrastructure, which makes it efficient and fast. And that's when we get to the topology, right? So typically, hypercube, that's, you know, very often used. I will have another one, enhanced hypercube. That's what make it, again, you see the planes, right? We go across that, all the data are moving as fast as possible. And that's what is our current limits. So we will end up in the 4,000 cores, 64 terabyte memory. And I just want to mention, the machine is ready. Also, the next one is ready for mic architecture. I'm originally an engineer. I believe it's pretty good. I program Zalog 80, so you can guess my age. And, they use this vector unit, scar unit, and that doesn't need a special programming. This small things in the corner is very important. It's x86 compatible. So if you create your application and run on the normal chip, it will run on mic, The integration between the mic and other cores, that's where Intel is very active, and that's really where all the issues again are running, right? So if you create I think the mic, the prototype which we have has around 32 cores. I think the first real products should have above 50, if I remember correctly. It is extremely important to know how to get this communication with the current standard CPUs, right? So you can consider, I call it, like a performance coprocessor. And how we handle the cluster. What is special on the cluster? Cluster are honestly the specialty and difficulty is how to make them big, reliable, and really practical. So what we do, that was our current generation. We have the new one. This is with the water cooling. I skip this. One thing what we learned on the previous generation was that the interconnect infrastructure is changing faster than the CPU infrastructure. So we decided not to integrate on the blade specific connection, and we have everything, all possible connections, on the mezzanine car. So we are much more flexible, right? Every time if the industry change the infrastructure connection, we don't need to redesign the blade. So it's again just for the cost effectiveness. And everyone now wants to have things sometime very high density. Honestly, I am not very happy. I can tell you why. You imagine you managing the data center. This machine is the high density machine, and you have to have, so comparing this, which is air cooled and can have the water doors, as we call it. This machine is cooled on every blade, right? So you can imagine everything get complicated, and the water with electronics is not going very well together, and you can imagine that all servicing things about that is also getting complicated. So we see now people, let's say, not pushing this too much because it may look, it's, let's say, good technology, running well, nothing wrong. It just get the things around complicated. The machine is fine, and again, you have to think about it, how you want to run the machine, where you want to invest the money. That's the cool thing, it's what we more do, we now put the things in the, infrastructure where you can see it's a cooling rack and D-rack, right? So D-rack means data rack, compute rack. So you have it like this, and you have the fans in between. So we shortcut the data, because today, if you can imagine that you have a 30 kilowatt, so if you put just, about, let's say, 20 machine, you have more than half megawatt, and you have then, if you want to cool it all by airflow, right, you have pretty stormy weather at the data center. And if you have it at the range of 18 degrees, it's very unpleasant weather, as you have seen last 2 weeks here, by the way. So this cannot even run up to 30 degrees, but it's shortcut, and all the cooling is going around, and 90% of all the heat is already solved here. We have much big, this is a huge ventilators, everything much more efficient. Technologies, where we go, again, that's in this machine, as I mentioned, we have the variants of what can be the connection board. We can go everything all to all. You would use it only for small systems. Typically, it's hypercube or enhanced hypercube. This is, here you have some. If one node fail, the application has problem. Here is much more safer. here is the most safer, but then, if you would have 1,000 nodes, you can all-to-all, you can multiply, you see the number of cables is unbelievable. And we do one more thing, not only that we develop all the NUMA, so we, again, on this whole machine, we use standard Linux. It is important to say you don't need any special Linux from us. It's a standard Linux because everything we made for NUMA, we make open source, so it's everything currently included. And what we else did, we have the OS noise synchronization. So why OS? So if you have 1,000 nodes, every node is, sometime computing, right? Sometime he need to make all his system management. And if you imagine, it's sure here is, exaggerated size, but if you imagine that 1,000, so it's like again the workers, right? So if you tell them now everyone go for lunch, right? So they go lunch, you lose 20 minutes, but then they work again. You can imagine if the 1,000 workers, each one of them decide when to go for lunch, and you need all of them, you have a problem. So we have, we synchronize the operating system. They do everything on every node. They do it at the same time. We allow them, when they can do the system overhead, we can achieve even another 20% of the performance was measured specifically by one of our customers. So some customers, as I mentioned, it's also important to know the examples. So NASA, as I mentioned, they are just now building. NASA have 3 football fields full of computers. With the service guy there, it's easy job, right? Because he go, and I mean, especially for the storage, they have such a big storage that he once a day pass the storage because there is absolutely sure there will be some failure, right? So it's not there waiting. It's a huge system. And that's in the Norway, just now installed new machines for the weather computation and also for scientific research in Norway. And that's why the climate is important. This is one lake in Iran, 2005, 2010. They say by 2015 it will be out. So there are big, significant things what impact our planet. And one of them are cyclones. If we can again just hit it. Yeah. This is just showing you the cumulative hurricanes. NASA is watching all the hurricanes going around. So you see it's hitting, here, the South Asia, it starts from Africa, right? And then hitting US. So again, this is all what is all time, monitored. You see, this famous, they have now, I think, Brita coming and so on. Why they watch it? Because every time, it's losing amazing money. So this is why I mentioned Cyclone, because we have one service which is called Cyclone. It's not, I don't want to go too much to detailing. It's Cyclone, it's a cloud for the technical computing. And, I'm not a big friend of, let's say, public cloud computing. I consider private cloud computing. Because for me, it's amazing, as I said as an engineer, for many years, everyone, when they want to buy a new computer, they analyze everything, look to memory, and now they say, especially the analysts say, you can run everything on a cloud. But the clouds are not optimized at all for your application. It's a, very standard machine, very standard nodes, how it will run. And why I show it, right? So there was one customer who made a test, and this is the result, on Amazon. And honestly, Amazon, the cloud is running on us. So I cannot blame Amazon big way. But that's, what they calculated, right? So that's a conclusion from mechanical engineering on Cyclone, right? And on Amazon. And as you see, in Amazon, you add CPUs, and nothing happened. So I just want to say that again, technical computing especially is not about you just put, another example, you just put together some nodes, right? You put the nodes intelligently together and you also, make all the parameters around. So this is very important. So in cloud, I believe, as a person, I believe you can do on cloud the very, very what we call stupid things, which don't require anything, or you can do very, very complicated things, like the expertise as a service. So you're already buying things, or let's say using, which someone already used his head, right, to make it practical. All the things in between, honestly, I don't know. And if I sometimes hear that the big company have to outsource everything because they have to focus only one thing, I sometimes feel then they don't understand how to run the business, really. And I guess, you know, in the HPC you want to have things balanced, right? So such a combination is not very practical. And we know how to avoid such a combination. So with that, I just have a logo. If I was clean enough.